Hello everyone and welcome to the lecture video for the first chapter in General Chemistry, Chem 101. So the first chapter in our Gilbert textbook is Particles of Matter, the Measurement and Tools of Science. So this chapter is just going to cover kind of a basic review of chemistry terminology. I'm going to make sure we're kind of all on the same page as the semester starts. Some of the topics that you see here listed in the overview we'll be sure to cover in lab, in our very first lab. However, the learning objectives you do see at the front of every set of slides applies to that set of slides. So hypothetically, for chapter 2, I may have 2 sets of slides. So anytime you look at this first page of slides, it's always just going to have the learning objectives that have to do with this specific set of slides. So if you're ever looking for something, that's a great way to just kind of pinpoint and tell where the information you're looking for is. So that being said, we're going to talk a little bit about what matter is, how to distinguish between pure substances and mixtures, homogeneous mixtures, heterogeneous mixtures, elements, compounds, that kind of a thing. We'll also talk a little bit about physical processes and chemical changes, as well as physical and chemical properties. We'll get to talking about, of course, the 3 states of matter and what we call those transitions, as well as what those transitions and those states of matter look at the macroscopic level. So when we're looking at it with what we can experience and feel with our eyes in the real world, versus what's actually happening at that particulate level, at that atomic and molecular level. As well as we'll talk just a little bit about the scientific method in these slides as well. So you can also find these learning objectives at the front of the chapter in your Gilbert textbook, and that will help you to determine as well the best information to read and kind of what to go over. It'll help you kind of focus in on the work that we're going to be doing. So, what is chemistry? Chemistry is a science that seeks to understand what makes up the world around us and why things exist the way that they do. So when we're talking about chemistry, we're really trying to get down to the nitty-gritty details about why is the world the way that it is when we're talking about the substance and the stuff that makes up the world. We want to know how we can investigate and manipulate the materials around us. So meaning like how can I actually study the things that are around me, as well as how can I try to change or do something to that stuff as well. That's kind of what differentiates some of the areas of chemistry that we might talk about as you start to specialize in chemistry. And we look at all scales of the universe. So we're going to talk about how electrons, protons, and neutrons make up atoms, how these atoms come together to form molecules, and how those molecules eventually become large scale and the world we see around us. So what's kind of tricky about chemistry and what can be hard to wrap your mind around is that we're going to be moving through these different scales throughout the semester. So I've kind of put the names of the 3 different scales that I'm going to be talking about and using quite often. You'll hear me talk about the subatomic scale or the subatomic level. So what's going on inside an atom? So that would be, again, electrons, protons, and neutrons. What are happening to those as they're making up an atom? Or maybe we're transferring an electron or something like that. We might talk about the atomic and molecular level or atomic and molecular scale. So what are individual atoms and molecules doing and how are they interacting? So maybe we're not caring so much about each individual subatomic particle, but this is more thinking about if we're completing a chemical reaction, we might have 2 molecules that react together to form something else. You might call this the reaction level as well, but we aren't necessarily always going to be studying chemical reactions. We'll also spend some time with just some substances kind of hanging out as they are without actually going through a reaction process as well. So that's kind of what I mean there. And we'll also talk about the macroscopic level. So what is happening at that full scale level that we can see and interact with in the real world. Because remember, there are lots and lots and lots of atoms and molecules that make up the amount of space and stuff that we can see with our eyes. So what I want to remind you is that chemicals do compose ordinary everyday things. So we often hear no added chemicals and chemical free on commercials. What does that even mean? Come on, what a joke. It frustrates me every time. My parents have told me to shut up when we're listening to commercials because they're like, I don't want to hear you. I don't want to hear you get mad about it saying chemical free again. Because chemicals make up everything around us. Atoms are chemicals. And they are the building blocks of the universe. So you, your dog, your car, your house, the table you're sitting at, the most pure water you could drink, the sun, the Mississippi River, the coffee you have every morning just to live. It's chemical. All of them are chemicals. Even your DNA is a chemical. Everything you see at the store is a chemical. So if you can feel, see, touch, smell, or otherwise observe it, you've got a really, really good argument that it's a chemical. There are a few technicalities that we'll talk about and we'll cover throughout the semester, but there are lots of good arguments there that we can call almost everything a chemical. So just be skeptical anytime you see that being advertised to you that way, because technically it's not true. Maybe they mean no harsh chemicals or something like that. That could be a fair statement, but chemical free, I think that sounds like BS. If you're selling me something and it's chemical free, I'm going to be upset because it sounds like you're selling me nothing in the end, right? All right. Okay, so we're going to talk a little bit about the scientific method here. So we want to know how we study chemistry. So we said chemistry is about the stuff that makes up the universe and how we study it. Let's talk a little bit about the scientific process that comes along with studying things in chemistry. Then we'll talk just a little bit about what chemists are actually really studying. So the scientific method kind of goes as follows. It may seem kind of trivial to be going through this because you're thinking, Professor Thomas, I learned this in 4th grade. Why do we got to talk about it again? Because it's really important to have this in your mind because this is what we will be using and moving through. And this is going to be just a little bit more of a grown-up college adult version of the scientific method. So first and foremost, the scientific method starts with some form of observation. So you got to notice something and ask why. And you take some sort of measurement to help guide your thoughts in that. So one kind of very important observation that a scientist made was by a biologist called Fleming. He was studying bacteria in his lab. He had a bunch of petri dishes, kicking it, set out, did all his bacteria swabs, left for the weekend, was expecting to come back to his lab with growth in his petri dishes, and he was going to check out all the bacteria in his petri dishes, except for the fact that he walked up to one of his petri dishes and it had a mold in it instead of the bacteria he expected. So he decided to make an observation then, start to take some tests, because this petri dish should have had bacteria in it and it only had mold in it. So 1, where did the bacteria go? 2, what is this mold? 3, how is this mold doing this? Where is my bacteria? How did the mold kill all the bacteria? And so he continued on through the scientific method that we'll talk about in just a second here. But the thing is that by stopping and making that observation and kind of asking why and then continuing to start to take some measurements to inform his thoughts, Fleming actually in that moment discovered penicillin, one of the great medical discoveries that has moved humankind further in society. So it was all done by accident. They think that potentially someone else in the building was studying molds and it went through the vents, happened to just boop, land in his petri dish where he was growing bacteria, and the rest is history. So it's just crazy to me that even some of the biggest discoveries in the world can be made entirely by accident. But scientists also can choose to decide what they observe and kind of go from there to kind of come up with some thoughts and things like that. So once we've had this observation, the next thing we do is make a hypothesis. So this is using the information gathered in the observation to make an informed prediction about what you actually observed. So it's not a random guess, and the best hypothesis is falsifiable, so it could be proven wrong. Lots of times scientists gather data attempting to prove an old hypothesis or an old theory wrong. So again, you're using the best information you have, the information you gathered to make an informed prediction about what you observed. Once you have a hypothesis, you can't just say, boom, I'm done. Hypothesis made. I did an observation. I did a hypothesis. Psh, must be right. One case it worked. Nah, that's not how it works at all. So in experimentation, We do want to complete experimentation after we have our hypothesis. So experimentation is actually a set of extremely highly controlled observations designed to confirm the hypothesis or prove it wrong. So these are going to be things where you've kind of done all your checks, you've run through all of the different possible scenarios in your mind, you have controlled everything that you can going into this experiment. It kind of gives you more solid proof, and you should always try to do as much experimentation as you can in different scenarios, because the more information you can gather, the more data you can gather from your experimentation, the better supported your theory or your final statement will be in the end. So it's very important that your experimentation kind of has all the holes plugged, and that you've got just about everything you can think of in place for that. So once we've completed our experimentation, we'll be left with a set of data, some form of information gathered, whether it be the color of solution, whether it be temperatures, it could be concentrations of solution, it could be anything, right? Some sort of measured piece of information that has come out of the experimentation. That's what we're going to call data. So once we've finished our experimentation, we've collected a bunch of data, we now need to analyze that data and complete an analysis step. So we're going to interpret the data from the experimentation phase to determine if the experimental outcomes support or nullify the hypothesis. So you can't just do the experimentation, leave a set of data out there for someone and be like, all right, cool, I did it, I did the experimentation, I'm done. Still not done yet. You have to be the one that analyzes the data and puts forth that information so that anyone can quickly read through the hypothetical paper you're publishing and see that either your experimental outcomes support or do not support the hypothesis. So the analysis step is really important, and there are lots of rigorous things you should go through during the analysis step, but we'll talk just a little bit about more about that during lab throughout the semester. Once you kind of have all of this information, you've decided whether your hypothesis is supported or not supported by your experimentation. The last thing you should do is come up with a theory or a model or a law, or have some way to present a summative statement about your findings. So you want to make sure there's some way where you're wrapping it all up, you tie it up with a neat little bow, and you say, all right, cool, I finished my experimentation, I finished my analysis, this is the information it supports, and this is the claim that I am making about that, and here is how you can use this in future experiments. So again, it's meant to bring all of the information together from that observation step through the analysis, and it helps you be able to communicate your results to your peers as well as potentially the public even, right? We see lots of scientific studies talked about on the news. Be skeptical of those regardless, because if you look at some of these steps, they didn't cover all their bases. So keep that in mind. But you may need to communicate your results with peers in the field. So you got to have some sort of statement where they can check to see if maybe this paper is going to be useful to them, or if they are able to build off of it in some way, shape, or form. And a good level of experimentation leaves you with space to kind of predict what's going to happen in the future. So if you're building a theory, model, or law, those things can be used to inform potential future experiments, where, for example, Antoine Lavoisier came up with the law of conservation of mass. And so we can use that law to continue to make predictions about what is going to happen in a chemical reaction. The law states matter is neither created nor destroyed during a chemical reaction. So the same stuff you start with is just the same stuff you finish with, just in a different pattern, in a different arrangement to make different molecules. So basically, we can use that to say, okay, cool, I know that this is what I started with, I know that this is what I ended with, so this is how much I should have in the end. So we can use that to predict for any chemical reaction in going forward. The last step in the scientific process, my personal favorite step in the scientific process, is revision, okay? So no scientific claim or no scientific anything is ever set in stone. We're always waiting for more data or more information to prove what we know false. So if any one of these steps is proven wrong, partially false, they can always be constantly revised to match the most recent experimental data and observations. So if you think about it this way, um, if we weren't working with revision and we decided that science was always set in stone the first time we had an idea, we would still think that the Earth is the center of the solar system, and a lot of our physics and a lot of our understanding of the galaxy and the universe and all the bigger structures out there in space around us wouldn't have that information, because we couldn't have figured that out if we still thought the Earth was the center of the solar system. Whereas we've moved to a heliocentric thought process about the solar system, so that we think that now everything rotates around the sun rather than around the Earth, and that unlocked a whole new area of science for us, and experimentation to do with astronomy and physics. So therefore, if we're not proving things false, we're not pushing science forward. We don't know everything as much as we act like we're the super advanced civilization that knows everything. A lot of things still happen by accident, and a lot of things are still not completely understood. And there'll be plenty of those situations that we talk about throughout the semester. So keep that in mind. And there's also a really, really good graphic about how the scientific method works on page 17 of the textbook. So go ahead and check that out as well. But always be revising, man. Always be revising. So that is how chemists study. It's how all scientists study. But what do we study? So chemists are out here studying matter, atoms, and molecules. So there may be many different kinds of matter. For example, all of the elements on the periodic table and the molecules they make up. So we need to kind of get some handles on what we're talking about when we're discussing these things. So matter is anything that occupies space and has mass. So that means it's got to have it takes up some amount of space, and it has mass. So there's some amount of stuff to it. So it takes up space and it has stuff. So you might also think of this as anything that has volume and mass, for example. So it includes extremely large items like planets and galaxies, and extremely small items like air particles or even the dust in your house, because I know that I need a dust for sure. That's kind of the idea there, is matter is just kind of all of the stuff we interact with. Atoms are submicroscopic particles that are the building blocks of the universe. So what do I mean by submicroscopic? That was not one of the scales I pointed out earlier. Basically, that's going to be your atomic molecular level is what submicroscopic means here. So submicroscopic particles, basically I can't go to a biology lab, grab their microscope, boop, pop it on, and be able to see that there are atoms and molecules that exist. That's kind of what I mean, is that they're below even that scale of where cells are, because cells are made of atoms and molecules. Lots of them. So that's kind of the idea here, is that they're teeny tiny particles. And they're the smallest grouping of stuff that can be distinctly categorized. So you should have taken some chemistry before you've been in this class, so you're probably not that unfamiliar when I say proton, neutron, and electron. We know that those are the subatomic particles, but the thing is that you can't tell which atom an electron belongs to if it's just floating out and about by itself. It's just an electron. But when we group those electrons, protons, and neutrons together and we make an atom, we can tell different atoms apart from each other. So it's the smallest grouping of stuff, aka subatomic particles, that can be distinctly categorized. So all matter is composed of atoms, and it's going to be all of the different elements you see on the periodic table. So those are your smallest building blocks in the universe, are all those little squares arranged on the periodic table. We'll also be talking a lot this semester about molecules. So we'll have two or more atoms joined together in a specific geometric arrangements. So molecules are held together by different kinds of chemical bonds. What I mean by that is molecules are held together we categorize their chemical bonds depending upon which two atoms are bound together. And different arrangements of atoms in different molecules have different macroscopic properties. So If you have H2O, you have water. If you have H2O2, you have hydrogen peroxide, and those behave entirely differently from each other. So different arrangements of different atoms are going to behave differently in their chemical properties. And we'll talk about a little bit more about what those are in just a second here. And they also always follow the law of constant composition. So every sample of a particular compound always contains the elements in the same proportions. So every time we have water, we have H2O. Every time we have H2O2, we have hydrogen peroxide. Every time we have H2SO4, we have sulfuric acid, and so on and so forth. So we always know that if we're talking about a specific chemical formula, we are talking about the same molecule, and we're expecting all of those elements to exist in the same proportions. And that's something we can count on as well. So chemical reactions are kind of the last little kind of definitional guy we got to get out of the way here before we move into some of the more interesting things like categorization. Chemical reactions are the transformation of one or more substance into completely different substances. So a chemical reaction takes a set of starting molecules, and in the end will end up with something entirely different. So anytime you start with one thing, end up with something else, you've got a good case that you've got a chemical reaction. Okay, so let's get down to a little bit more of the nitty-gritty here. Some of the more interesting things we're going to talk about. I mean, it depends upon whether you find this interesting or not. But let's talk about how we classify matter. So we talked a little bit about what matter is, atoms, molecules, chemical reactions. Let's talk a little bit about how we classify that matter and kind of classify those things and what's going on with them. So oftentimes science deals with classification just to tell different things apart. And let me tell you, humans love to categorize things. I personally am like a huge categorizer. Like, for example, my closet is all by sleeve length, then by color, because that's how I decide what I'm going to wear in the morning. I ask my Google what the weather is. I decide what sleeve length I'm going to wear, and then from there, I decide what color I want to wear. So that is kind of, one way we might categorize things, but we're going to talk about how to do the same thing for matter as well. So we're going to classify by the type of matter first, and then we're going to talk about how to classify matter by state. So classifying matter is useful to know exactly what's being studied and how it can be studied. So if I know something is in a certain state of matter, there are a certain set of assumptions about what the particles are doing at that atomic molecular level that I can make as long as I know what's going on. So making that classification will help me to understand at a deeper level what's going on with the stuff I'm using, as well as it's very important to know the composition of matter to determine how it must be treated for experimental purposes. So like, you don't want to experiment on something that is that you like think is pure, which is actually a mixture, because imagine that could have some really unintended consequences. If you've got something in your mixture that you thought was pure and you didn't know it was there, oh boy, I'm almost certain it'd ruin your reaction, and hopefully you'd still be living through that. So it's so important to know what you got going on so that you can make better decisions with the matter that you're working with. So the first thing we're going to talk about is classifying matter according to composition. So when we do this, we're classifying matter according to the stuff that it's made up of. So this could be in the two broadest categories: pure substances or mixtures. So pure substances are made up of only one type of thing, whereas mixtures are made up of two or more types of things. So let's talk about pure substances first. So again, pure substances are made up of only one thing, so one type of atom or one type of molecule. So if you only have one type of atom, that's an element, right? That's like all these guys here on the periodic table. These are all elements, right? So those are all just one type of atom. They cannot be broken down into any smaller grouping. It's just one type of atom there. However, if you have only one type of molecule, we'll call that a compound. So it's a substance made up of two or more elements, but it only has like that molecule that exists there. So this might be things like water, table salt, sugar, so on and so forth. Molecules, aka compounds in this instant, are a bit more common than elements are, because a lot of times the elements are naturally mixing and reacting with each other in everyday life. If you have a pure substance, you either have an element or you have a compound. Is it atoms or is it all one molecule, one type of molecule? Okay. The other broad category that we have when we're classifying matter according to composition is a mixture. So this is made up of two or more kinds of atoms or molecules. So if we have two or more kinds of atoms or molecules mixed together, we might have a homogeneous mixture or a heterogeneous mixture. So a homogeneous mixture or a homogeneous mixture, I learned to say homogeneous, you're more than welcome to say homogeneous. But a homogeneous mixture is a mixture that is consistently mixed all the way through. So it doesn't matter where you draw the sample from, it's all going to be the same stuff, the same ratio of the components. So for example, if I go to the Dead Sea, right, and that's salt water, it's like a ton of salt in the water, so much salt that we can float on top of it because we are less dense as humans than that salt water is. But it doesn't matter whether I go to the north of the sea, the south of the sea, the west, the east, I'm at the top of the sea, I'm at the bottom of the sea. It's going to have that same ratio of salt in it to water. It doesn't matter whether you draw my blood from my left arm, whether you draw the blood from my right arm, my hands, anywhere in my body, you're going to find that my blood is mixed consistently all the way through. So homogeneous mixtures, again, are just mixed consistently all the way through. It doesn't matter where you get the sample from. You'll find that it has the same composition no matter what you look at. However, in contrast, heterogeneous mixtures have a composition that is varied by region. So it's not consistently mixed all the way through. So a more chemistry example is to talk about oil and water, right? So I might have some oil and some water in a jar together. You might have noticed this sometimes in like salad dressings. They can kind of separate out and you'll see like the oily part at the top and the watery part at the bottom. So it doesn't matter if I like take that bottle and I like shake it. You'll see that there are distinct regions where the oil exists, distinct regions where the water exists. So it really matters where I draw the sample from. And if I let it settle out, I'll see that oil at the top, water at the bottom. So it really, really matters where I'm drawing my sample from. An easy way to kind of visualize this and think about it, I like to think about a Supreme pizza, right? So Supreme pizza's got like 4 kinds of meat, all the veggies, right? So if I take my first bite of pizza, I'm going to take a bite and I'm going to get like pepperoni, sausage, cheese, sauce, bread, right? I go to take the second bite and I finish that piece of pepperoni. I now have an olive and part of a mushroom, as well as that cheese sauce bread. And as I keep working my way through and I eat all the way to the crust, I'm going to get to a point where there's just the crust, just the bread at the bottom or at the top of the pizza. So what I'm trying to say here is like that's not consistently mixed all the way through. It depended upon what flavors I got in each individual bite that I took as I was eating the pizza. And even in the end, we have that region around the edge of the pizza that's all just the crust. So to me, that's an easy way to think about it is like if you can find those distinct regions where you're going to have different flavors of what's there, that is going to be a heterogeneous mixture. So there is a really convenient flow chart on page 5 of your book, but it's going to look something similar to this. I just didn't have access to some of the graphics from the book before I made these slides, but I've contacted the publisher, so I'll get access to some of the graphics and I'll put them directly into the slides in the future. But this is a very similar picture, as well as I like too that it shows us what's happening on the atomic molecular level as well. What we're thinking about here is matter first and foremost, and we're thinking about how it can be what's going on. The first things first is we take our matter and we decide whether it's a pure substance or whether it's mixtures. So can it be separated out by some physical process? Nothing to do with chemical reactions, but can it be separated out by a physical process? And we'll talk a little bit more about physical processes in just a second, okay? So can it be separated by a physical process? This is one question you can ask yourself to determine if it's a pure substance or a mixture. Or I like to think about, do I have all of one thing or do I have some representation of different things? So if it's a pure substance, you can look at it under the question, can it be decomposed by a chemical reaction? So is it a molecule or is it an atom? We could decompose molecules by chemical reactions to get them back to their original just atomic elements. And if we're thinking about mixtures, again, we have that question, is it uniform throughout? If so, it's homogeneous. If not, it's heterogeneous. So You can see some atomic level depictions of these at the bottom too. Here we can clearly see that this is an element because they're all different, or they're all the same color atoms here, and they're all just atoms, and we see that we just have one thing hanging out here. Versus when we're looking at a pure substance that's a compound, we can see that we have one type of molecule, and we only have one type of molecule. However, we see that it is a molecule. It is something that could be broken down further, decomposed by a chemical reaction, but we only have one type of molecule, so we can still consider that to be a pure substance, but we're going to call it a compound instead, because we can see that we have red atoms, black atoms, and white atoms. The red are always going to be oxygen, the black ones are always going to be carbon, and the white ones are always going to be hydrogen. So all sugar is made up of is carbon, hydrogen, and oxygen in the end. So pretty neat. And if we're checking about that mixture side of things, if we have a homogeneous mixture, we can see that this is relatively consistently mixed all the way through. I wish we could zoom out a little bit more and see a few more molecules to prove that. But here we have our buddy sugar over here appearing in the tea. We've put some sugar in our tea. We've got some water molecules, and we have one of the molecules that comes from tea itself. So if I took a sample of that tea at any point in time, anywhere in that tea, I would find that I have a consistent mixture all the way through. And if I'm looking at like a heterogeneous mixture, this oil and water mix over here, we can see that we've got lots of these water molecules, one red oxygen, two white hydrogens, water, with some oil molecules at the top, these long carbon chains with some hydrogens on them. So we can see that there are two distinct regions here. Where heterogeneous, that indicate that this is a heterogeneous mixture. Let's go ahead. We're going to work through actually a couple of problems using this flow chart so I can kind of show you some typical things you might want to think about when we're classifying matter. If I want to classify brass is a mix of copper and zinc. It's what we would call an alloy, a mix of two different metals. So it's a copper and zinc alloy. So if I have copper and zinc mixed together, that already tips me off that I have some sort of mixture. But if you think about brass, one place you may have seen it before is like with brass instruments, right? If you think about a trumpet, there's no distinct region on a trumpet that looks different than anything else, right? If it's all brass, it's all looking the same way through. Brass is a consistent mixture all the way through, so brass is a homogeneous mixture. So if I'm thinking about the next example here, cereal in milk. So when I make my cereal, I'm going to pour my bowl of Lucky Charms. I'm going to pour the cereal in. I'm going to pour some milk over top of it. And as I continue to eat my cereal, I'm going to have different regions of mixture, right? I could eat all of just one type of thing. So like, Lucky Charms has like the pieces and the marshmallows. So I could take one bite that has all marshmallows. I could take one bite that has marshmallows and milk. I could take a bite that has pieces, marshmallows, and milk. I could take a bite that just has pieces. In the end, I'm going to have, I could just like push my spoon down so I could just get milk, or I could drink out of the bowl. We're going to start to see, as I start to eat, I'm going to have a dry section at the top. I don't pour that much milk into my cereal. And I'm going to have a more milk-saturated section at the bottom. And as I continue to eat, the cereal will go down and join that milk-saturated region of my cereal. I don't know why I'm being so technical about cereal. You already know it's a heterogeneous mixture because there were so many different ways that I could eat that cereal, and I could have different samples depending upon whether I was drawing from the bottom of the bowl, just the milk, top of the bowl where there's dry cereal, which pieces I was getting, the pieces or the marshmallows. Copper in milk. Cereal in milk is a heterogeneous mixture. Okay, so I'm going to work through just one more here with you. I do have all of the answers to these listed on the next page over. So if you have any questions, you can go ahead and kind of guess and check with yourself as well. Or if there's something you're like, dude, what do you mean? I wouldn't classify it that way. You can always inbox me on Canvas, and I will wonderfully answer your questions and see if we can't work out kind of any misconceptions you have going on. So the last one I want to talk about right now is water. So if I list something like water, I think it's fair to assume it's a pure substance. I'm not saying anything else is mixed in. So I would say water is a pure substance, but we have to determine whether it's an element or a compound in that case. So remember, water is made up of 2 hydrogen atoms, 1 oxygen atom, H2O, our bestie. So water is H2O. So we're going to consider that to be a compound, right? We could break it apart into its individual atoms, hydrogen, 2 hydrogens, 1 oxygen, but in the end, it is a compound because those things are bound together. So again, if you want to work through the rest of those yourself, I highly recommend that. And then you can find all of the answers to these questions in the slides as well. So we have one more area of classification to talk about here. We want to classify our matter according to state. So matter actually exists in 4 states naturally, if you want to use that word. And that would be solid, liquid, gas, and plasma. However, in this class, we're only going to talk about solids, liquids, and gases, and we're going to leave plasma for the physicists there. We let them handle that. It may seem really, really obvious, like Professor Thomas, states of matter. I am in like general chemistry in college, and we're going to talk about states of matter. You're kidding me. I feel you. However, we're actually going to get down to how the state, or like to define the states of matter by how those atoms and molecules are interacting with each other. So what we're going to do is we're going to look at the freedom of movement of atoms and molecules compared to one another at that atomic molecular level. And we're going to shift our focus to what's actually happening at that level rather than the broad scale levels we tend to experience. I will definitely equivalate it to that. However, it's more important that I want you guys to learn now how to define these 3 states of matter based upon the interactions of those molecules. Because remember, we can make certain sets of assumptions about the matter itself as we're studying it based upon the state of the matter. So let's talk about solids first. So in a solid, atoms and molecules are packed close together in fixed locations, okay? So I've got a picture of a solid down here in the right-hand corner of your screen. So you can see that these are like relatively ordered rows. Oftentimes, that's what a solid will look like. Oftentimes, that's what a solid will look like. And again, you can see how tightly those are packed together. They're basically touching, if you want to consider it to be that. So I'm going to talk about the solid, liquid, and gas forms of our bestie water. So water's solid form is ice, okay? So if you want a comparison, water's solid form is ice. So within this rigid structure, what might happen is that those molecules are going to be wiggling and vibrating around, but they are held in a fixed position. So even if they're wiggling or vibrating, they are not free to move outside of this structure that they have been placed in if they are remaining a solid. So it's a rigid shape that does not change no matter the container. So I could put an ice cube in my water bottle. I could take that ice cube out. I could put it in a Tupperware container. I could take it out. I could drop it on the floor. It's still going to be that same shape the entire time. It's not going to change. And so we'll also start to relate solids, liquids, and gases to temperature as well. So as we're doing this, we'll find that solids exist at the coolest temperatures for a specific substance, okay? So certain things are solids at room temperature, but we got to put water in the freezer to make ice, so it's a little bit colder there. So this is just relative when we're talking about temperatures, just relative to the substance. Everything's going to have a different point where it's solid and a different point where it's a liquid and a different point where it's gas. But we're just talking about relatively solids are going to be at the coolest temperatures. Okay, and remember their atoms and molecules are locked in that close together fixed location, even though they may vibrate or wiggle just a little bit within their place. So this is my little solid dance. If you see me doing this, we're talking about solids. I can tell you that. It's my solid dance. Wiggle, wiggle, wiggle. Okay, So liquids. Liquids are atoms and molecules that are closely packed together but can slip and slide past each other, okay? So water's liquid form is, spoiler alert, water. That would be the word we would use for that. In a liquid, the atoms and molecules, they're still going to be touching each other and they're still going to be interacting, but they slip and slide past each other. So it always reminds me of the motion of the ocean. You know, anytime we have a liquid, the atoms and molecules are kind of doing this. Reminds me of the waves of the ocean. The ocean's a liquid, so I'm sure that's why it reminds me of it. You can see a picture of what liquid atoms and molecules look like down here. So they're still touching. They're still extremely close together. They're super packed, but they do have that little bit more freedom of motion, whereas our solid just sits in place and wiggles. Our liquid kind of does this, where the atoms and molecules, they're touching and they're interacting, but they're slipping and sliding past each other. Liquids take the shape of the container, but don't expand to fill the container. So what do I mean by that? I could take the water in my water bottle that is currently the shape of my water bottle. I could pour it in a Tupperware container and it's going to fill the bottom of that container. If I pour it into a popcorn bowl, it's going to fill the bottom of that bowl there. So it's going to take the shape of the container, but you know, it's not like the water's like floating up to the top to like fill the entire container like we're in the International Space Station, right? That's not the way this works. So it's not expanding to fill the container, but it's going to take the shape of the container. Whereas, you know, when we had our ice cube, it didn't matter where I put that ice cube, it was still going to be a cube, right? Whereas with liquid water, you're seeing that it's going to fill the entire container. And so to relate this to solids, solids occur at the coolest temperatures and liquids are kind of the mid-range temperatures for whatever that substance is. So again, liquids, they are still closely packed together. They are still interacting and influencing each other, those atoms and molecules, but they can slip and slide past each other. So our last state of matter is gases. So gases are atoms and molecules that are separated by large distances and they do not interact with each other. So they are free to move however they wish because they are not close enough to be influenced by other atoms and molecules. So you can kind of see that in the picture down here in comparison, right? So our solids, they're all touching. Our liquids are all basically touching too, those atoms and molecules. Whereas in a gas, they're not even close. Gases are like doing this. They're flying around just bouncing off whatever they run into, and that is it. They're not influencing each other. If each of my hands is like a gas particle, it's just bouncing off, only influenced by its container, really. Gases actually do fill the shape of their entire container. So gases can expand and contract, right? We have a little bit of experience with this. You know, you wake up on a cold winter morning and it kind of feels like your tires are a little flat when you start out. That gas is contracting a bit. As you start driving and you warm your tire up, it'll feel like it's back to normal and that gas is expanding, right? So gases fill the entire shape of their container. So if I have a couple of gas molecules and I put them in my little teeny tiny Tupperware container, they're only going to move as far as they can within that container, but they're going to be bouncing off all of the walls of the container, right? Not just the bottom like a liquid, and they're not keeping one specific shape like a solid. If I go ahead and I take those same couple of molecules and I put them into my fridge and I shut the door really fast, right? They're going to be bouncing around inside my fridge. And they can fill up my entire fridge. If I go ahead and I open the door and I let them out into my entire apartment, well, they're going to bounce around off all the walls and expand to fill my entire apartment, no matter how many molecules I have. So this ability to expand and contract is called compressibility. So we call gases compressible. So a substance is compressible if you can remove space between the atoms and the molecules. So, because gas atoms / molecules are so far apart, you can push them together for a while before they actually become close enough to start interacting with each other. So if I've got like this much space, I can push them in and they're still not interacting, push them in, they're still not interacting until I finally get them so tight under pressure that they become a liquid. Remember that this is due to the fact that there is a large amount of space between gas molecules. So solids and liquids, they're not compressible. There's not enough space in this liquid or in this solid for there to be any space in between those atoms and molecules removed. Here, there is so much space that we consider gases to be compressible. They have this ability that you can remove the space in between the atoms and molecules. So here's just a quick summary slide if you want to be able to review solids, liquids, and gases. I didn't mention on the last slide, I apologize. Gases do tend to exist at the warmest temperatures relative for a substance. So again, remember, I'm just talking relative to a substance. And the gas associated with water is water vapor or steam, depending upon which word you use. So again, solids are going to be at the coolest temperatures, liquids are going to be mid-range, and gases are going to occur at whatever is a warm temperature for said substance. So again, this is just a summary slide. If you want to go back and kind of talk about all of the different features of solids, liquids, and gases, and I've got comparable pictures down here for you too. So if we have states of matter, we can also transition atoms and molecules into these different states of matter, right? And we call these phase changes when a substance changes from one state to another. So when matter changes state from one state of matter to another state of matter, we call those phase changes. I'm going to run through these really quick. Most of them should be familiar to you, but I'll focus a little bit more in on the ones that might not be so familiar. So freezing is going from the liquid state to the solid state. It's associated with a decrease in temperature, right? If we want to freeze water to make ice cubes, we've got to get water from the sink, put it in our ice cube tray, put it into the freezer, let it sit for a while to have that temperature decreased enough that those atoms and molecules slow down enough that they can become in the solid state. Melting is just the opposite of freezing. So if something is melting, it's going to go from the solid state to the liquid state, and this is the opposite, so of course it's associated with an increase in temperature of the substance itself. Condensation, so this is going from the gaseous state to the liquid state. So condensation isn't only a noun, it's a verb as well. So it's not just the stuff you see on the outside of your glass on a humid day. It's the process that water coming from the air happens where it's a gaseous water in the air and it condenses onto the outside of your glass. So it's associated with a decrease in temperature. So that glass is much colder than the air around it, so that gaseous water ends up becoming liquid water on the outside of your cup. Boiling is the opposite of condensation. So it's going from the liquid state to the gaseous state. So it's associated with an increase in temperature, right? We put a pot of water on the stove, we turn the stove on so that the heat from the stove ends up causing the water to boil and go from a liquid to a gas. So the two that may not feel quite so familiar that get me every time are sublimation and decomposition. So sublimation is kind of cool because under certain sets of circumstances, you can go from a solid directly to a gas. No liquid needed. No stop in the middle. Do not pass go. Do not collect $200. Goes directly from the solid state to the gaseous state. So it's associated with a sharp increase in temperature, and this is what dry ice does. So dry ice is frozen carbon dioxide, so it's just immediately going from that solid brick up to a gas. And deposition is the opposite of that. So deposition is going from the gaseous state directly to a solid state. And it's associated with a sharp decrease in temperature as well. So if you think about it, if you breathe on a super cold window in the winter, which of course we can do here in the Midwest, if you kind of go and you breathe on that window, what's going to happen is you can start to see some of the liquid vapors from your breath solidify on that window, and you can see that they'll make like really, really beautiful snowflake-like crystal patterns. So if you want to try that out sometime in the winter, it's still a little bit too hot. We're more in the condensation section right now with the level of humidity we deal with in the summer. So deposition, again, is going from a gaseous state directly to a solid state, and it's associated with a decrease in temperature. So if you breathe on that was my example, was breathing on a cold window in the winter. So these are the phase changes. They're transitioning between states of matter. I think it's important for you guys to know what each of these means, as well as whether it's associated with an increase or decrease in temperature of the substance. Okay, so I got a little quiz here for you. It's an opportunity for you to test yourself. So the question is, which image best represents matter in the gaseous state? And I want you to think about how you know this. What characteristics of the picture show you that it is in the gaseous state? So go ahead, pause, and then we'll come back together and I'll talk about the answer. Pause, please. All right, so let's go ahead and talk about the answer here. So picture C is going to best represent the atoms in a gaseous state, right? So these atoms are very far apart from each other. They're not interacting with one another, right? Whereas A and B better represent solids and liquids, because here you can see that a solid has all of these atoms in rigid rows. And the liquid here, you can see that there's a little bit of space, but there's a lot more opportunity for motion, but it's not quite so spread out as the gas. So just a little bit of an opportunity for you to get to quiz yourself and get to know kind of how I'll ask some questions on homework assignments. So what else can we learn about matter, right? So we talked a little bit about phase changes. We talked a little bit about how to classify matter according to state, classify matter according to composition. What else are we interested in? So we're going to talk a little bit about the properties of matter and changes in matter. So matter has characteristics that can be measured with or without some sort of change to the substance. So properties are characteristics that we can use to distinguish one substance from another, right? Like we can see that gold looks gold and silver looks silver. You know, if I'm trying to tell if a cup has isopropyl alcohol or it has water in it, I might waft. We'll learn this in lab, but I might kind of bring the smell up to my nose and I can tell which one is the isopropyl alcohol and which one is the water through smell. So these are properties of a substance. So a physical property is a characteristic that a substance displays without changing its identity. So it's how the substance kind of behaves as itself. Like, how am I going to measure something about the substance while it's just sitting there, hanging out, doing its thing? So these might be things like color, density, volume, mass, boiling point, melting point. So the points at which that occur are physical properties attached to each substance. And so on and so forth here. Chemical properties, in contrast, are a characteristic that a substance displays when it's changing its chemical composition. So it's how a substance behaves as it changes into something else when it doesn't have that same chemical makeup. So these might be things like toxicity. So how is that chemical interacting with your body? Is it creating something that is harmful to your body? Is it chemically stable, right? So how long can I leave it sitting on a shelf before it starts to naturally decompose and turn into something else? Flammability, how easy is it to light on fire? So on and so forth. So that's kind of the difference between a physical property and a chemical property. So again, properties are just characteristics of a substance. They're a measurement of something of the substance. But physical properties are how that substance behaves as itself, and chemical properties are how substances behave as they're turning into something else. So We talked a little bit about properties of matter, but what can be sometimes more interesting is not only to measure those properties, but also to observe changes in the matter, right? So a physical change is matter when it changes its appearance, but not its makeup. So this is what a physical process is. When we were talking about separating pure substances and mixtures earlier, you can separate mixtures through physical processes or physical changes. So again, a physical change is when matter changes its appearance, but not its makeup. So you still have what you started with, but it might just look a little bit different. So different form, same substance. So if I took a pop can and I crushed it, that's going to be a physical change. If I boil some water, physical change. I melt some ice, physical change. All of those different phase changes are going to be physical changes. If I shred some paper, that's going to also be something like that. So again, it's just for some reason it looks a little bit different, but in the end, it is the same actual chemical makeup of the substance. As far as chemical changes go, well, that's when matter changes its composition, right? So physical change, composition doesn't change. Chemical changes, boom, of course, the composition changes. So it may or may not be accompanied by a visible change. I can think of plenty of different scenarios, like if I'm mixing NaOH as a solution and I'm mixing HCl as a solution, so a strong base and a strong acid, I start with two things that look just like pure clear liquids, but when I mix them together, I still get a clear liquid. So there's no visible change that something has happened, but I've gone from having a strong acid and a strong base to having salt water in my beaker when I mix them together. We'll talk more about acids and bases later in the semester. We'll even do something in lab with them as well. If you've heard of titrations, they're my favorite. I'm so excited we're going to do them this semester. So again, in the end, even if you can't tell what happened, you don't have the same thing you started with, and maybe in that situation where you can't tell what happened, we can do some sort of measurement on the substance to see that it's changed, right? So you do not have the same thing you started with. In the end, you have something entirely new. So this might be burning wood, digesting food, cooking an egg, milk going bad, metal rusting, and of course, chemical reactions. So in the end here, you've got the physical changes that have the same composition before and after, and you have chemical changes which have a different composition before and after. So the contrast here in properties is that properties are kind of a measurement of the substance, whereas changes, we're talking about it actually kind of moving its form somehow. So one last test yourself here, and then I'm sending you off to work on your homework and so on and so forth. Let me move myself down here in the corner. Hello. So what I want to know is which of the lighters here is undergoing a chemical change, and how do you know that? So go ahead, take a look at these lighters. What could show you that there's a chemical change versus a physical change? And then go ahead, take your time, pause the video. So pause now. And see if you can't answer this question for yourself. So go ahead, pause that video, see if you can answer the question. And in 3, 2, 1, I'm going to go ahead and answer the question now. So you've been warned. Try to figure it out yourself first. All right, so which of the lighters here is undergoing a chemical change, and how do you know? Well, it's the lighter on the right. So if I look at what starts inside the lighter and what is happening outside the lighter, I can determine that this has been a chemical change. So in the right-hand lighter here, I see that I have liquid butane inside, but when it's lit on fire, I see that I have carbon dioxide and water molecules. So here's my carbon dioxide, 1 black carbon, 2 red oxygens, and a couple of water molecules. So 1 red oxygen, 2 white hydrogens there. So it's getting some oxygen from the air, and clearly it's not the same molecules that started at the bottom of my lighter, right? So at the bottom of my lighter here, I have something entirely different than what's at the end here. So if we want to think about why the left-hand lighter might represent a physical change, this is like when you actually push the button and strike a lighter and you actually light it, Whereas if you don't hit the wheel and you don't strike the lighter and you just push the button, you'll find that you have liquid butane on the inside, and all you're doing is releasing that liquid butane into gaseous butane outside outside the lighter. So you can see down here, I have the same molecule, all of just these carbons and hydrogens hooked together inside the lighter as I do outside the lighter. However, you can see that this is a liquid. Those molecules are relatively tightly packed together, interacting with each other, the best that we can depict in this situation. Whereas up here, we can see that they're spread out far apart from each other, so we can see that that represents a gas and a physical change. So that is it for chapter 1. That's kind of what I expect you to know. Again, it's a lot of background information. You've probably had some contact with this stuff before, but please, please, please let me know if you have any questions, if you need any more information, and I will get that to you ASAP. Always inbox me on Canvas. That is the absolute best way to contact me. All right, I'll see you back for some later chapters.